So last week we began the class with the definition of cooking from the Oxford English Dictionary, who defined cooking as the transition of food under the application of heat. You will recall that we recast that definition as a plot because we're scientists and we like to make plots. And so we plotted the temperature on an axis, and we drew a line, and we said below some critical temperature, the food is uncooked, and above that critical temperature, the food is cooked. We also are able to, on that plot, put different foods. And so, for example, here is the phase diagram of an egg. So you know that below some critical temperature, an egg is uncooked. An uncooked egg is essentially a liquid. You can sort of shake it up and down and feel that it's a liquid inside, whereas a cooked egg, when you cook it above some critical temperature, it becomes a solid. If you make your eggs in a scrambled fashion, if you make a poached egg, if you make a hard-boiled egg, however you make it, when the thing is cooked, it is solid. And so there's a transition from a liquid to a solid at some temperature. Now, you will also recall that Dave Arnold, in his discussion of eggs, showed us that actually that there are many critical temperatures inside of an egg. And in fact, if you're trying to control the texture of an egg to make it feel perfectly for you, you sort of have lots of different choices. If you like slightly runnier eggs, it's sort of 60, 61 degrees, sort of overcooked eggs, at least according to Dave, that was 68, 69, 70 degrees, whereas the perfect egg, maybe that's at about 64 degrees. And the reason, so really inside of a single food, in this case an egg, there are lots of different transitions. There's not just one transition going from uncooked to cooked. There are many different transitions which correspond to different things. Now, as we will see in this course, those different things correspond to different molecular transitions in the food. And so, for example, with respect to an egg, there's a molecular transition that occurs at 63 degrees Celsius where a protein named avotransferrin unfolds, and that's one of the reasons that the egg changes texture as you go through that temperature boundary. Now, and as you increase the temperature, there are more and more transitions. Different molecules undergo different things, and that's just the way that cooking an egg is. But it's not just eggs that have this sort of complicated phase behavior. I mean, if you were instead interested in cooking something else, like, say, a turkey, it is also the case that as you increase the internal temperature of a turkey, there are many different types of phase transitions that occur that are really at the root of the reason that the texture of turkey and even the taste, to some extent, feels different when you cook it to different temperatures. The same is true with other foods like a pie or a cake. Depending on how long you cook your pie and what the internal temperature is, there are different transitions and different molecular events that occur. And in this class, really one of our goals is going to be to explain what those transitions are, to explain why they occur, explain how to control them, to make yourself a better chef. And this will all be in the context of these sorts of phase diagrams that we're showing you now, where there are different things that occur when you hit different threshold temperatures. What we would like to do to start our investigation is to study something a little bit simpler than an egg or a chicken or a turkey or a cake. These are, of course, the foods that we love to eat, but they're a bit complicated in their physical behavior. And so what we're going to do right now is to start out and just compare the phase behavior of eggs and other foods to those of simpler materials that you at least are more familiar with. Perhaps the most important material for all of us is water. This is because we're mainly composed of water. All food is mainly composed of water, and water is really perhaps the most ubiquitous substance around us in our daily lives. It is also true that water in itself plays an important role in cooking. When you cook your requisite hard-boiled egg, a typical way to do it is to put it in hot water. And also, since food is composed with water, when you heat it up, one of the things you're doing is heating up the water. So for that reason, the phase behavior of water is really an important backdrop to this entire course. But it also really poses an important example to compare and contrast different phase behaviors. So with that as an introduction, this is the phase diagram for water. And what happens is very common. You all know that this is what happens, and we're just making you think about it right now in the context of one of these plots. Namely, there is a critical temperature, which is about 0 degrees Celsius, below which water is a solid, it's ice. And there's a critical temperature above which the water transforms from a liquid to a gas. And you all know that that occurs at about 100 degrees Celsius, at least if the pressure is 1 atmosphere about sea level. And in between these two temperatures, that is the temperature where water is a solid and water is a gas, water is a liquid, and that's the liquid that we drink and love so much and are composed of. Now, what's so interesting about this actually is when you compare the phase diagram to water with the phase diagram for an egg, and they look totally different. Whereas water actually is a solid when you cool it, an egg actually becomes a solid when you heat it. It looks exactly backwards. When you heat water, it boils and it becomes a gas, whereas when you heat an egg, it basically becomes a solid. And so how can this be? How can it be that the phase behavior of one material, an egg, is so different than the phase behavior of another material, namely water, which actually, as I already said, is a critical component of egg? And the reason, as we will see, is because of some very special things that happen inside of the molecules of an egg. But for now, in order to sort of delve into what's going on, what I want to do is to go through a couple of other materials that are sort of simple materials in the same way that water is. They're pure materials. They only are composed of a single substance. And I want to look at the phase behavior of those materials, and let's see if it looks more like that of water or more like that of an egg. So actually, before I do that, let me sort of just mention one other thing, which is an important difference between water and egg, which is the following. If you take ice, for example, here in Boston every year it snows, and then there's this wonderful spring day that arises. It's inevitably going to arise where the snow melts and the ice becomes water. So the ice, that's an example of a reversible transition. I mean, if you put water in your freezer and it becomes ice, if you take it out of the freezer and leave it outside, in the ambient air, it will of course melt and become a liquid. In contrast, if you cook an egg, if you hard boil an egg, and you transform it from being a liquid to a solid and you leave it out on the counter, it will never, ever become a liquid again. It's done. It's a solid. Similarly, if you cook a turkey, the turkey does not uncook itself. It will always remain a turkey. If you cook a cake, it never reverts back to its previous state. Whereas if you freeze water, then it will revert back. Actually, here's something you could try to do while you're listening to this lecture. You could go to your refrigerator right now, and if it has eggs in it, you can take out an egg and put the egg in your freezer and close it and come back. Make sure you position it carefully so it doesn't break all over the other food in your freezer. And what you will see is when you come back to your freezer at the end of having done the exercises, et cetera, for this entire week of the course, that the egg will have frozen and it will be a solid egg. It will be a little cold. It will feel differently than a hard-boiled egg just because of the temperature of the shell. But if you let it warm up a bit, then it will be a solid egg, and it will feel essentially identical to that of a hard-boiled egg. However, if you put it on your counter and let it sit, then it will also return back to being a liquid. It will reverse back. And so there's something weird about the fact of heating the egg that actually makes it become a solid. And we will come back to that in due course. But for now, in order to sort of delve into what's going on, what I want to do is to go through a couple of other materials that are sort of simple materials in the same way that water is. They're pure materials. They only are composed of a single substance. And I want to look at the phase behavior of those materials, and let's see if it looks more like that of water or more like that of an egg. So the first material I'd like to show you is nitrogen. Now, nitrogen actually is a very important aspect of your daily life, even if you don't know it, because nitrogen is actually the major component of air. So most of the gas that's around me and around you is composed of nitrogen, and it won't surprise you, therefore, to know that at room temperature, nitrogen is actually a gas. You can make nitrogen into a liquid if you cool it enough, and it turns out that the temperature at which nitrogen transitions from a gas to a liquid is about minus 195 degrees Celsius. So it's very, very cold. If you cool it a little more to about minus 210 degrees Celsius, then nitrogen will become a solid. So nitrogen has a phase behavior that looks actually, for all intents and purposes, a lot like that of water. At high temperatures, it's a gas. At low temperatures, it's a solid. The difference is just that the critical temperatures are different numbers, that nitrogen becomes a liquid at much colder temperatures. And indeed, actually, as you will see throughout this course, some of our chefs are experts in using nitrogen to cause transitions in foods, that is liquid nitrogen. And what they use is the fact that it's so cold, which allows unusual transitions. So here's another material that's important for cooking. This is ethanol. So ethanol, of course, is something that many people like to drink. If you're enjoying or not enjoying today's lecture with a glass of wine in your hand, then, which is recommended, by the way, then the wine, of course, has some amount of ethanol that's in it. Ethanol, therefore, it won't surprise you to find out it's a liquid at room temperature, because otherwise there wouldn't be liquid ethanol in your wine. So the temperature at which ethanol transitions from being a liquid to a gas occurs at a slightly lower temperature than that of water. It happens at about 78 degrees Celsius. That's why alcohol boils off more quickly from a dish than water. If you're ever using wine or something to make sauces, we will come back to that later on too in this class. Ethanol also can become a solid, and to do that you have to cool it more than you have to cool water. The temperature at which ethanol becomes a solid is about minus 114 degrees Celsius. But the point that I want you to take away is that the general phase behavior of ethanol also is exactly like that of water, and it's exactly like that of nitrogen. It's just that the transition temperatures are changing, and in particular, it looks nothing like that of an egg. So it seems that the peculiar substance is actually not water, nitrogen, ethanol, it's the egg. So these phase diagrams, and I include the egg in this, that is, pose a very important question about physics, which is what we have to think through now, which is, why is it that the different materials have transitions at the places that they do? So why is it that water transitions from a liquid to a gas at 100 degrees Celsius? Why does it transition from a liquid to a solid at 0 degrees Celsius? Why do these numbers change in nitrogen? Why does nitrogen have to cool it so much for it to become a liquid? And so on and so forth. And what we would like to do is to develop reasons why. We would like to be able to think about the material and have some understanding of why it has the phase behavior it does. And the reason for this is because that will help us to understand the physics of not only the materials that these simple materials, but ultimately the materials that we cook with. And that's what we're about to start to delve into in more detail. But before we do that, I just want to leave you with one final example, which I think is also an example that's important for cooking, but is an interesting one because it shows something else that can happen. And that is the example of carbon dioxide. You know that carbon dioxide is a gas at room temperature. Every day in the newspaper, it seems there's another article about the concentration of the ever-increasing concentration of carbon dioxide in the atmosphere. If you cool carbon dioxide enough, it becomes a solid. There's actually no liquid phase at 1 atmosphere. And the temperature at which this happens is minus 80 degrees Celsius. So the phase diagram of carbon dioxide, if you look at it, it sort of appears strikingly different from that of water. Namely, at high temperatures, that is above minus 80 degrees Celsius, carbon dioxide is a gas. At lower temperatures, that is below minus 80 degrees Celsius, carbon dioxide is a solid. So there's no liquid phase in the carbon dioxide phase diagram. Now, solid carbon dioxide is something that you've also probably experienced. That goes by another name, dry ice. But what's interesting about this, from the present vantage point, is that this is an example of something which becomes a gas at high temperatures, a solid at low temperatures, but there's no liquid phase. And so our goal is to start to expose how this can be and why this is and why different materials have the phase behavior that they do.